start, I would like to mention that TIFR has been very instrumental in my own personal journey, life journey. So I am always very happy to come here, and I would like to thank, I guess, the surroundings for that. So today, what I will tell you about is a new, what I believe is a new kind of ground state.
So Jubilan,
yeah.
For the recording, it's better to stay in
this chalk
between the two.
Okay.
Right.
Okay. So ground state or vacuum or vacuum, because there's going to be many degenerate ground states. So just to motivate where I don't fully know where it fits, I would like to give, let's say, my perspective on how one can think about some scheme of classification. So one well-known class is spontaneously broken condensate, spontaneous symmetry, broken condensate, right? So one of the best examples is superconductivity, and this has generally, if it is a continuous symmetry, some gapless Goldstone modes, and there can be some gapped modes also, and generally they may be described, generally speaking, by some some Ginsburg-Landau framework of field theory. So another general class is, we can call it many-body topological order. So for example, example would be, so a famous example is Kitaev toric code. But more generally, there's this whole class, Levin-Wen models, string nets, and then there are these fracton models. So it connects to something called higher form symmetries, on which I'm not really an expert. And these ones, generally speaking, have some exotic excitations. So some anionic excitations. So then a third kind is not sort of symmetry unbroken liquid-like state. Liquid-like ground state. So a good example of this is quantum spin liquids. So which the models I'll talk about will probably have something to do with this. And these are generally, so I forgot to mention that these often, in terms of field theory, sometimes Chern-Simons theories are used to describe, for example, quantum Hall effects.
Are you making a distinction between quantum spin liquids and topological orders here?
Yeah.
Quantum spin liquids have topological order.
It can.
Right?
It can have.
Chern-Simons description, but
Right.
some emergent gauge field and there's
Correct.
some
Correct.
light excitation.
Correct. So that's what I was going to mention. So in terms of gauge theory thinking, there is some emergent gauge field or gauge theory.
But sorry to be so ignorant, can I ask? Typically, the second category, Chern-Simons descriptions,
Yeah.
they are gap phases.
Yes,
right?
yes.
And
I
is
forgot.
that true for the spin liquids?
No,
It can be both ways. Right?
they can be both
So
ways.
if your C2 descriptions, they are gap.
Right.
U1 descriptions will be gap.
Right. So that's the distinction. That's why I was not putting in with this, because there can be gapless phases which need not have which need not have topological order. Yeah.
No, but so I have this question. So the U1 spin liquid has topological order or not?
I don't think so.
Doesn't have.
Yeah.
So this word, this topological order, what
Yeah, I
exactly is
never
that?
understood exactly how to do it.
What is
So you need
topological
ground
order?
state degeneracy depending on the torus you put it on.
Right.
Topological, depending on the topology.
Yes.
Is that one
I see.
definition?
That's a perfectly fine definition. You put it in some torus, you should have some degeneracy. U1 spin liquid is a unique ground state. Yeah, liquid-like.
Fixed number of degeneracy doesn't depend on the size of the
Yeah,
system.
yeah.
But that may not be the property of such spin liquid. Right?
Yeah.
The ground state degeneracy may depend on the size also.
Right. So you can have gapped spin liquids, and gapped spin liquids often can have topological order actually, or gapless. So what Kedar?
Sorry, I'm confused.
Yeah.
If I
Yeah.
have a torus,
Yeah.
like a U1 spin liquid,
Yeah.
I can talk in terms of the U1 flux threading the holes of the torus, no?
Right. I can.
And
Yeah.
that's not a ground state degeneracy. I mean, after all, the way I think about the Z2 ground state degeneracy, I
Right.
say there is either a Z2 flux there or not there. So
Right. No. So this is this whole Oshikawa-Hastings LSM theorem, right? So either if you have gap, then it's topologically ordered. It must be. But otherwise, you can have gapless. Then you can have a unique ground state.
But then,
No, he's asking, suppose you thread a flux, U1 flux
Yeah.
through the whole of the torus.
Right.
Does that give you another ground?
Only
state?
when you remain gapped throughout the process.
But it is still deconfinement.
Huh?
It's still deconfinement.
Yeah, but if you have a gap ground state and if you do this, then
Then another ground. That's
right,
fine.
right. But when you have gapless, you can't say anything through this argument. Yeah.
No, but practically,
No, but
pneumatics
I thought-
and just thread
no,
it
no,
up
but-
flux and seeing what the.
Okay, maybe this is just a different definition, but
Uh-huh.
U1 spin liquids also have fractalized excitation.
Correct.
So in that
Correct.
sense, they have topological order.
I mean,
Oh, so this is some.
I don't think of it as top.
degeneracy.
Yeah,
Okay.
yeah,
Sure.
yeah. So, sorry, you were saying?
I'm saying,
Huh.
has anyone looked at,
Huh.
let's say, if you actually
Uh-huh.
thread a flux,
Yeah.
numerically how, to the extent that
I
you
see.
look with financial.
Yeah.
Is it very close or?
Yeah. There has been a study, I think, by
And
Paul.
the usual statements are once it's gapless, you can't say anything for sure.
Right,
That doesn't
right.
mean it can't be.
True.
Sorry,
Sense in which you can talk of degeneration.
True.
But sorry, just to understand, so you take one of these spin liquids which are
Mhm.
which is gapless,
Mhm.
thread a flux, and then you want to see
Whether you get a new
what
ground
happens
state or not.
with the flux in place.
Ah,
Yeah,
ah,
Yeah,
ah,
like,
ah.
does it go to a very high energy state or it's
Yeah.
almost close?
Yeah.
I don't know.
Yeah. Yeah.
But maybe you could look at other measures like topological entanglement and
Right.
Correct.
That there is.
Correct.
No.
So that's a good comment. There are spin liquids without any topological entanglement entropy. So that's a good comment. Yeah. And then finally, I hope this is visible, what you can call this, where SYK model, I was just writing the model, the example, and essentially there is no quasi-particle description.
I mean, just to say that, just the non-fractional quantum Hall effect also doesn't have, it's a gap system, it has a Chern-Simons description,
Right.
but it has no topological entanglement.
But
I see.
background.
I see.
Yeah, but I mean, in the same spirit in which the fractional does. So I'm just saying, it's not going to come,
Yeah, this is not a very sort of strict classification or anything. So this SYK model have gotten very interesting because they don't have any quasi-particle description to begin with, and of course they have connections to quantum gravity.
Many-body topological order, an example is just something described by Chern-Simons theory.
Generally speaking, yeah. So quantum Hall effects, yeah. So when I actually contacted people here, because I didn't mention it, but from the title, these constructions will have extensive ground state entropy. So a lot of degenerate ground states. So it kind of reminded me of this because this model also has an extensive ground state entropy in a certain limit. But now I have, let's say, softened a little bit, and actually in a way it's more interesting because I don't know where these models that I'll talk about fit. Whether it,
Why do you say they have extensive ground state entropy?
Which one?
Which
one? You think that
SYK in a
No,
certain-
not SYK. You were saying that the
Gold
same
star.
things happen there.
no, the things that I'm going to talk about.
Is quantum.
Okay.
Yeah.
So none of those that you have written. have
No.
before SYK.
So this was just to motivate what I'm going to talk about, where it fits. Yeah.
So in what sense SYK
you know, if you take the limits in a particular way,
Right.
if you take n, you know, the number of
So it's
limits,
between n.
yeah,
Yeah,
you
yeah.
go to infinity first.
Yeah, you have to take n
before
going to
you
infinity
use-
first. Yeah.
then there's actually-
Yeah. So the simple, well, one way of looking at it is that you always have lot of small energy modes, regardless of what you do.
I think Abhijit was asking how can quantum mechanics make sense?
Yeah.
That's what I was
Sorry, I didn't follow that comment.
Meaning extensively normally think of in space.
Okay.
in
Okay.
number of
Number of, yes. I see. Got it. Yep. So today, the basic question is today's vacuum or vacua, where does it fit? So that's what I would like to sort of, maybe we can keep it in the back of the mind, and more precisely it has aspects of quantum spin liquids, and at least this sort of lot of low energy modes it has common with SYK. Whether it means it is a system with this property, I don't know yet. Another thing I forgot to mention, that this has connections to quantum chaos bound saturation because of this property. So few things. So the models I'll talk about.
I'm really sorry.
Yes,
I know
please.
It is already, but just because I'd love to understand this, what is a quantum spin liquid? I mean, when one says SYK model is distinct, can you just 2 minutes just say,
So quantum
if you don't
spin
mind?
liquid for me is, you have a system made out of the spin degrees of freedom, but for some reason any kind of order parameter that you can think of is never non-zero.
So
Any natural order parameter, it's a local order parameter. That's one sort of simple way of thinking about it.
Yeah, so that's the confusion, right? That's one way of thinking, and the other way involves some amount of logical order of factors,
Right.
etc. And it's not clear what is the connection of those two ways of
Right.
Logical order of what?
So, see, the prototypical example of a spin liquid could be the Kitai model. Now, the Kitai model also has topological order in the sense that when you put it on a torus, depending on whether there's a C2 flux through the holes or not, you get a different ground state, right? So there's 4 ground states.
So in particular, spin liquids are gap systems?
Not
Yeah,
necessarily.
yeah, also-
Not necessarily.
Not necessarily.
Yeah.
So you can have gapless photon degrees of freedom in a U1 spin liquid.
Yeah.
Right?
Yeah.
Whether the spin excitations are gapped or not is a separate question, but there can be singlet excitations that are gapless and
Correct,
modeled by a
correct.
photon of
Right.
defined U1.
Right.
For
Yeah.
example.
Yes.
So the phenomenological description of a spin liquid unfortunately is a negative one.
Mhm.
What doesn't happen? No
Yeah.
ordering clicks.
Right. But
Just
But the theoretical description can involve these other ways of thinking, and at least in my mind, there's no clarity about how the two connect. And this is, but people know this. I just don't.
And when you have these gapless degrees of freedom, then to talk about topological order is a clear thing?
No,
Not always, not
Exactly.
always.
That's the
Yeah.
confusion.
Yeah.
You're asking even for gap spin liquids,
Yeah.
which may be easier to define
Right.
and classify.
Right.
Like at least in that case, is there a clear notion of
I think
Yeah.
you don't
disconnect?
It can-
No.
yeah.
The connection between absence of
Ah.
actual order parameters, we understand,
Aha.
versus the
Ah.
fact that there
Ah.
will be a topology.
Aha.
Yeah.
Aha.
These two
So I don't
equivalent
want to
statements.
logically deduce one from the other.
Hmm.
All the examples I know
Hmm.
have both.
Yeah.
I've not seen one where you logically.
I mean, all the examples I know, if they're gap and are
Yeah, well, yeah, right.
phenomenological sense, also have topological.
And there has to be, like fractional excitations are also involved in this.
That comes in the
That
topological.
comes with
So
the-
there are excitations to contribute statistics?
Yeah.
Yeah.
In the Kitai model, there's the horizontal.
So one simple thing we can already say is that if it's if it is like continuous symmetry broken, you will always have gapless modes. So suppose if it is gapped, then it cannot be any continuous symmetry breaking. That we can already say. Whether there's some discrete symmetry breaking, for example, Ising model or something, is always
Also,
possible.
You have to
Yeah.
rule out bond ordering, you have to rule out singlet sector
Precisely. So okay.
discrete symmetry,
Yeah, yeah.
lattice.
Yeah. So it is not.
I mean, let me just say that Shubhro gave some set of lectures on this, which apparently makes this all very clear. and they are on video, and I was hoping to watch them with some students every Thursday starting next week.
Yeah, yeah. I don't think there is any one-to-one correspondence.
Coming on 26th.
So we can ask him.
So we
But apparently he gave
Send me the
some-
schedule for these lectures.
We're going to watch it on video.
If you guys are there.
Yeah.
So okay, in this
Where do the antiferromagnetic spin chain fit in this?
spin chain,
Yeah, or let's say whatever lattice.
so two-dimensional stuff fit here, like where you actually have magnetic ordering, and spin chains are a special class where you don't
But in
order.
Antiferromagnet you don't have ordering, right?
No, of course you are watching.
Up, down.
Yeah.
But let's say some frustrated kind of thing.
That may or may not have ordering. So then, if it doesn't have ordering, it would fit here.
There's nothing topological about that then, right?
It may or may not. So these are not like a distinct, they're not disjoint categories. Yeah. So
One question, I think for gapless, you have Fermi liquids where
Right.
currently no usual
Huh.
local order parameters is there.
haha, haha,
And you can construct other order
Right.
complicated.
right.
So, how would I distinguish a gapless spin liquid from a Fermi liquid, let's say?
A Fermi liquid.
Gapless, nothing is ordered by this definition.
So
Well, that's where the excitation comes in, right? Spin
Yeah.
class.
yeah. So in general, quantum
So
spin.
it can't be just about the ground state. That was my. That's where I was directed.
Yeah, that's the reason to mention this excitation column at some level. Yeah.
Phenomenologically, you would say no ordering in the ground state and funny excitation.
Yeah.
So
Yeah.
how can we define both gapped and gapless quantum spin liquid as a quantum order? Not a full
Yeah, my problem is I don't know what that means. That's a
These
what.
are all PSG classification and all.
That's okay.
Yeah. So
It is zoomed as one of.
So you seem to know. So what? So how does he?
Should I stop or-
PSG.
But PSG somehow have to do with some movies, and then
Symmetry.
Yeah, but he sort of classified all these gapless and gap on a quantum model, the beyond the topology model.
So yeah, one comment is Kitaev's spin liquid is a very sort of good
This
toy.
is category theory and that kind
No
of
category.
You are not doing category
No,
theory?
no
Okay, I need to learn something new there.
Yeah. So in Kitaev's spin liquid or Kitaev honeycomb model is a good toy model, because there you can just constructively see these things, that there is no ordering of any kind apart from whatever the Hamiltonian wants to have. So there is no broken symmetry. You can constructively show this, and it turns out the models that I will talk about also you can constructively show this somewhat technically more interesting, because it does. At least I don't know how to have an exact solution for these models. Yet there is enough structure to sort of make statements of that sort. So with that, I'll move towards.
Recording
So one is, it's not clear what are the nature of excitations. Then this we were discussing in the car with Kedar, but I think it's a motivated question. Is there a field theoretic framework for all of this? And the answer could be that maybe there is none. And then the other thing is, so as I mentioned, this has extensive degeneracies or exponential, so extensive entropies. So what is the consequence of that? Sort of physical transport type consequences of that. These things are also sort of not, I don't know the answers to them. And one can also, there is a statement, there's a bound which is called Haas bound. So this is a bound on the amount of degeneracy you can have in a given system if it has topological order. So there is a notion of something called homogeneous topological order, where all these, essentially you can think of some kind of string net Levinman models if you know them. All the known classes of topological order, they satisfy a bound on the amount of degeneracy you can have in the ground state manifold, and it is never extensive, it is sub-extensive. So based on that, I believe this stuff is not many body topological order, even though it might have some other kind of topological order which I don't know about. Ha. Have you heard of Ha's code? So like Kitaev code, there's it's like factons and all that. Yeah. Okay, so with that we'll move towards the results.
So here extensive, you by that you mean extensive in volume.
Extensive in volume. So the degeneracy is exponential in system size.
So this is all in the model you're going to test.
Correct.
And is your model gap to gapless?
Don't know. So that's why nature of excitations. Yeah. So it's
I have one question.
sorry.
Are the statements you are making robust to perturbations?
Uh,
I'll give you one answer. I
uh.
take the Hubbard model. I don't go to higher order in. I just go at the 0th order. I can
Right.
talk up to the power.
Right,
You
right.
can broken as I go.
Right.
Do it better and better. And
Right,
so on and
right,
so forth,
right.
So is it a fine-tuned model or?
I don't think so.
Can you please write down the model? How many dimensions? Just, I mean, I can't begin to think about it.
Sure.
I'm sorry.
Sure. Yeah.
Some of us are saying this because we have seen them.
Oh, okay.
But
I see.
others have not.
Yeah. If time permits, to your question, there is one case which is solvable like a Kitaev spin liquid and actually fits into this class. So if time permits, there I know the nature of excitations. And more generally speaking, my belief right now is that it should be gapless. That's my belief. Okay, so before I write down the actual models which are not solvable, I would just like to motivate it by some simpler things where we can solve things. So let's take the following model. So it's like an Ising model. So let me draw a lattice. So I have a chain, an Ising chain. And I have some auxiliary degrees of freedom. You can imagine it to be infinite. And you can compare it to a standard Ising model.
Sorry,
Yeah.
Second term is sigma zi nearest neighbors?
Yeah, so like
I is nearest?
this neighbor,
Oh,
this
okay,
kind of
auxiliary.
neighbor.
Okay.
Correct. So this is the standard transverse field Ising model, and this has some kind of similarity to it. So you can imagine it as if you are applying the transverse field through these auxiliary degrees of freedom.
So the auxiliary is a dynamical.
It's a proper degree of freedom.
And
Yeah.
how many
So your
dimensions?
infinite degeneracy here is going to be lifted as soon as I put in tiny coupling between those boundaries.
Precisely.
Right.
Yeah.
So it's not pathological in that sense. I can add some epsilon.
Yeah.
Your infinite
Yeah.
degeneracy will go.
Infinite degeneracy will go away, but the corresponding physics won't go away.
That's possible.
Yeah.
So it's just a linear chain?
It's just a linear chain. Yeah, this is just to motivate the statement. So, okay. So, first of all the.
This works in D dimension, right? I think that D
Yeah.
dimensional system and I add spins on top.
Yeah.
As long as I can do that canonical transfer.
Correct. So the point is this is solvable, so it's useful to instructive to look at this. So first of all these models have the standard what we call Z2 symmetry.
Just to understand, there's no dynamic, no Hamiltonian directly for the boundary guys.
In this one, only through,
the
yes.
fine tuning.
Yeah, that's a fine tuning, exactly.
So after I just think of it as an effective field, I just push sigma.
But dynamic.
Huh?
But dynamic.
Dynamic.
Right, they're part of the Hilbert.
Yeah. Basically you are guessing the subsequent few statements I am going to make. So all of them have the Z2 symmetry, which is basically, let's, if you wish.
Also on the chain, if I add sigma y, you're in trouble.
Yeah, I'm in trouble.
Maybe not.
Yeah. So.
All this trouble comments.
Exactly. What's the trouble?
What do you mean by
No, sir. I haven't seen this paper. I'm just commenting on the fact that I can rotate about the x-axis, and for each choice of the boundary spins, I can rotate it back to a uniform.
Yeah.
That's all.
But trouble means your nice properties go away. Is
Yeah.
that trouble?
Okay, maybe let me write down the nice properties.
Sorry, I mean, that's so
So the infinite degeneracy is all I'm speaking
Why,
about.
why do you have it then? I don't even see the infinite.
Yeah.
Let him get to the
I don't see the setups.
Yeah, so there is this property that I can prove, and then there is, let me just call it spin liquidity. These two properties I can prove. Okay, so by spin liquidity, any kind of ordering, spin ordering, you can show it to be 0. Okay, so let's get to this. So first of all these models have the standard Z2 symmetry, which is so there's a way to implement this, but if you take this to this, the H goes to H. So you get a symmetry out of it. And this symmetry forces on you the what is called the fermion parity.
And no transformation on the boundary spins or the auxiliary spins, or you do the same on the auxiliary spins as well?
I mean, that is not involved in the Hamiltonian, so if you wish, you can do
I'm
it.
just trying to make, so the symmetry transformation is only on the spins of
Right.
the chain.
Right. Yeah. Yeah.
But the boundary spins are in that. The del I is the boundary spin.
Yeah. No. This fact that sigma I goes to minus
So you're not
is not
changing
going.
the boundary spin, no
Huh.
transformation on the
Yeah.
boundary spin.
Yeah.
That's
I
all
mean, so if I understand, say this is what the x component does, z does nothing, it goes to itself,
Yeah.
I suppose.
Suppose.
Rotation by pi around.
Yeah.
Rotation
Yeah.
by pi outside.
And
Yeah.
that is the
Yeah.
lesson.
Yeah.
You could also have changed
You could have
boundary
done. You could have. It's going to become relevant. So that's not an irrelevant question. We'll see that freedom is what will give rise to the extensive degeneracy actually. So what the conservation law for this is, you have fermion parity, sometimes it's called, or the net magnetization modulo 2 is conserved. So in one dimensions you can do some fermionization, and in the fermion language it becomes a fermion parity conservation. So after you do the transformation, this becomes a superconducting Hamiltonian. So there's that conservation. So the new structure that is present here is the following. So clearly, H, these sigma z's are conserved. So all these sigma z's for all auxiliary spins is conserved. So that is evident. The only somewhat, I mean, you need to sort of realize it. The new symmetry is the following: sigma sigma x on these bonds. They are also symmetries, and this kind of construction is ubiquitous in the literature of exactly solvable models. So this is the trick.
What is it? So
Sigma x on these auxiliary
Oh, I
bonds.
see.
Yeah, this full set
for each I.
for each I, right? Yeah, exactly. So this is the new structure. Okay, these two are conserved quantities, and the new other aspect of this is that these two mutually commute, anti-commute. What I mean is, so only when they share a site. Yeah. So if they don't share a site, they commute. Okay. So if you have this, you can prove this property. So we'll go towards that.
What is double angular bracket for?
That they commute if they come from different sites, just to
and anti-commute otherwise, right?
or anti-commute. It's just a notation we can. Because I didn't know whether to say it anti-commuting sets, or the thing is right. So I just on-site anti-commute. Yeah. So why does it imply a degeneracy? So before we prove it, you can sort of think of it intuitively. So
I'm so sorry.
Yes,
Even
please.
the first statement,
Yeah.
I'm not seeing why. So if you did this commutator, you get one anti-commutator with the
Huh.
first guy,
huh,
and one anti-commutator with the second guy.
Guy.
So one looks like it produces a sigma y for the first guy, and the second
Huh.
was sigma y for the second guy.
Huh.
I don't see why it's zero. Sorry.
why this one? So sigma x and sigma z anti-commute.
Sigma x and sigma z.
With 2 minus sign. No, what I'm confused by.
No, I mean, don't you get an anti-commutator? Oh, anti-commutator. I see. Thank you. Yeah, right. Yeah,
It's symmetry because there are two minus.
Yeah. Thank you.
Yeah.
Use the anti-commutator, not the commutator.
Yeah.
Sorry, but that statement is H is commuting with that, right?
Yeah.
H commutes, but they
Two
use
anti-commutators.
generators anti-commute.
Yeah.
Write a commutator in terms of two anti-commutators.
Yeah.
Correct, precisely. Yeah. So here's the point. So we can, so if this is these are conserved, that means I can fix their quantum numbers, right? And then I can do a job, and then solve it. You solve it, right?
So basically, you fix the sigma z's, which
Right.
are the conserved quantities on the boundary.
Right.
And then if it's minus, I rotate by pi about the x-axis to make it plus.
Yes.
And I get I
No, but-
always map it. I can map any sector
Right.
to the uniform transverse field Ising J.
Precisely. That is a statement.
That's all.
That is a statement, but you have to rotate using this.
Yeah.
Yeah,
I rotate
yeah.
by pi about the
Using this. So you have to rotate the partner spin as well along the way.
I rotate by pi about the x-axis.
Yes, yes.
Whole system.
Not whole system, just on this bond is enough.
Yeah.
Ah.
Whole system money the pair. Yeah.
Yes, on the pair.
Degeneracy is 2 to the power L.
Exactly.
Yes,
Yeah.
that's why, because you do these individual rotations on each bond. That's, I know, So that is the trick.
And the fine tuning is you have no interactions between the boundary spins because that will
Yes.
the 2 to be a.
Right,
Yeah,
right.
Yeah, they'll mix all the sectors.
Yeah, so at students, was this point clear? Yeah. So,
Because L is the entire degeneracy of the boundary
Yeah.
Hilbert space.
of the full Hilbert space, of the ground state manifold,
Of this boundary space.
Right.
of the system. Yeah,
The 2 to the power L is just because each of these could be either plus or minus.
correct. Yeah, as simple as that. Yeah.
So each of what? I mean, there is a sigma z also, and then there is this other operator. There are two things, right?
But I think the argument, if I understand, just so take any set of values for sigma z on the boundary,
Okay.
then do this rotation and say turn them all to be
Yeah.
+1,
Yeah.
and then you'll have a ground state for that what's
Yeah.
being
Then
called
you get a
transverse
ground state of
field.
the uniform transverse field Ising J.
And so
Yeah.
in this way.
Yeah. Yes, please.
In fact, the whole spectrum is 2 to the n.
I mean, the algebra of these operators side by side is irreducible. It will damage.
Yeah, so this is probably,
I think
this,
that this, if you take this and this, and you make the algebra of that, there's a two-dimensional irreducible.
Yeah.
okay. So you mean for,
Pauli matrices.
for a single thing?
For each eye.
For each eye,
Because it looks
yes.
like Pauli matrices.
Yeah, for each eye, precisely,
eye.
precisely.
Yeah.
But from a physics point of view, you have to do this rotation, you have to do the rotation simultaneously on both sides. You
Yeah.
cannot just rotate one. Yeah.
Sure, but the question is that you've got a symmetry algebra on each side.
Yes.
So you want an irreducible representation of that. That's two-dimensional.
Yeah, exactly. So it turns out that you can work out the spectrum in this case, but
Yeah.
even when you can't work out the spectrum, you can use this structure to say things about the degeneracy.
Now I'm very confused. So if I choose the boundary spin,
Mm-hmm.
the sigma boundary
Mm-hmm.
to be plus, to be whatever they are, that's one sector.
Right.
Right? And so now in that sector, the Hamiltonian for the rest of the system has a Jz
Correct.
and a sign times
Right.
the sigma zi.
Very good. Yeah.
Right?
Yes.
Different signs. So
Precisely.
it's a random field in the z.
Right.
Now I want to make that random field go away and make it a uniform.
Right.
So I should not rotate the sigma zi. I should only rotate the boundaries.
No.
Otherwise, how will I make it all go away into
No.
the same term?
So the one way to think of it is you rotate this.
I only rotate the boundary is my claim.
No. You have to because this is the symmetry.
Yeah.
So maybe let me pedantically at least say it for the students. So how does the degeneracy follow? Just excuse me. So if you have two commutators, question. If you have two commutators or two conserved quantities, and if you have a ground state, this with, let's say we take this basis, then this state is also a ground state with the same energy due to the commutation, but under A it has a minus A, and this, if A is non-zero, this is a distinct ground state. That's a simple.
What is A?
This is more generally speaking. A are some operators, some general operators, just linear algebra. I'm just rephrasing it, right? So these are the two ground state, and so therefore it just, this degeneracy depends on the count of one of the sets.
Sir, just,
Yeah. A and B anti-commute. Oh, I forgot to write that. Thank you. Yes, please.
just to re-understand. I mean, at each eye there is a 4-dimensional Hilbert space. There's 2 times 2.
Correct.
And this symmetry, this algebra breaks it acts on 2 irreducible blocks of the
Right,
4-dimensional
right,
space,
right.
each of which is 2 dimensional.
Right. Exactly.
From every energy.
Yes.
No, it's not true.
Yes.
No. What you're saying is fine. The algebra makes sense, but now I'm having trouble just trying to do it by hand. If I choose all the sigma z boundaries to be some +1, -1, +1, -1, I fix that. Right? That's one sector. Now, what's the Hamiltonian in that sector? It's for the rest of them. It's a sigma x, sigma y plus some random sign times the sigmas.
Correct.
Right? Now that's the problem you have to solve in that sector. It will have some spectrum depending on the pattern of the random signs.
Right.
The claim is every state is 2 to the n degenerate, that means the pattern of signs shouldn't matter.
That is
How
the
do I make sure the pattern of signs doesn't matter? I rotate the sigma zi to make it a minus sigma zi. Therefore, I rotate the spin system by pi about the x-axis.
individual bonds.
At the individual
Okay.
basis,
Yes.
Side-dependent
Yeah.
rotation
Yeah.
of the basis of
Yeah.
the
Yeah.
system,
Yeah.
but not of the boundary space. Because those are +1, -1, whatever they are.
Right.
And I read that information and
Right.
I choose the rotations I do of the system.
But the state
So
also
I'm
changes.
only rotating the system by pi in a side-dependent way about the x-axis,
That's,
not the boundary space.
but that changes
But
the
your
boundary spin.
algebra somehow makes it seem like you have to simultaneously rotate.
Baba, you have to rotate because the action is by sigma
B psi, na?
sigma
No.
del
B psi.
ix, na?
Yeah.
No, but what is, so I don't
So
understand.
B psi, right, Kedar? So when, say,
The
let,
argument I gave maps every sector
Mhm.
to the uniform transverse field ICJ.
correct,
Therefore, every sector has the same spectrum throughout for
Correct.
all eigenstates,
Correct.
not just ground state.
correct,
So, therefore, the full problem has to do the degeneracy for every sector,
Correct.
every state,
correct,
right?
correct.
Now, I don't understand how this by hand argument gels with the claim that I have to simultaneously rotate both the boundaries.
Because of B psi. So you have to act by sigma ix, sigma partial ix on this bond.
That's my point, but I didn't seem to in this argument I just gave.
Oh, I see. You are saying that why it should.
I'm just saying
Mhm.
that I have +1, -1, +1, -1, some pattern on the boundary.
Mhm.
That is in the original basis.
Right,
I just read that pattern
right,
and I notice that that is causing my sum over I sigma zi to not be a uniform.
right.
sum,
Some random
with
sign.
some sign.
Yes.
So wherever I see a minus sign, I want to rotate that system sigma zi. Without doing anything to the boundary, I just want to rotate that system sigma zi, right? Canonical transformation on one set of spins,
Okay.
right?
Okay.
Which I do by rotating by pi about the x-axis.
Okay. For that site. Very good.
In this argument, what have I done? I've only rotated certain sides.
Correct.
System.
Correct.
I have not rotated any of the boundaries.
Correct.
But in your argument, I've rotated the boundary also.
But why was this rotation asymmetric?
Yeah.
No, I'm just saying I map every problem. So
Oh,
each
I see.
sector has a different Hamiltonian.
You
I
just
map all
relabel, relabel.
Yeah, I'm just mapping them all to the same Hamiltonian.
Same Hamiltonian.
Then whatever spectrum it has, every sector will have the same spectrum.
No, but relabel this
Why?
sigma x
Why?
being there. right?
No, I'm rotating by pi about the x-axis of the
He
system.
is only rotating the boundary.
Not the boundary.
Ah,
No.
that's where it fails.
Yeah. There is a.
No, then I rotate about the. No, I rotate about the x-axis. No, so the x doesn't change.
He is rotating the boundaries.
So what are you rotating?
I am rotating a certain set of sides of the chain.
Of the chain.
Of the chain, only of the chain.
Ha, very good. I see. Ah, that's what you mean by system. Okay, very good.
About the x-axis
Uh-huh.
by pi.
Aha.
Okay.
Why does
About
that?
the x-axis
So sigma
by
x
pi.
doesn't
So
change.
sigma x does not change
Does
because
not
I'm
change.
rotating about the x-axis.
Yeah.
When I rotate about the pi, that particular sigma zi becomes minus sigma zi.
Yeah.
That compensates from the minus sign that is there in the boundary spin in that sector at that site.
Yeah.
So all sectors now map to the same Hamiltonian,
Yeah.
which is the uniform transverse field
Yes,
Hamiltonian.
right.
Yeah.
Therefore, it has whatever spectrum it has.
No, but-
Therefore, I proved every state of this.
No, but
Bernoulli.
No, there's something
that's
off.
Another way to see this degeneracy, right? Because now that uniform field transient model will have, let's say, one ground state.
No.
You know, a whole spectrum, whatever.
Yeah. But let's say ground state.
Every state.
And then every state, and then you would have 2 to the n
That's what I'm
copies
saying.
of
But
copies
in
of that.
this argument,
But this is consistent.
No, there's something off. No, there's
what's
some.
confusing me is he's insisting that you rotate the boundary spin and and the
Right.
system spin together, I'm only rotating the system.
Yeah.
That is saying
There's something
that
off.
Another set of algebra. You
Yeah,
can-
I'll have to think about it. But there's something. There is some
I think you are
issue
also
there.
using the fact that this is the symmetry. when-
No, he is not using. He doesn't want to use that.
No, but when you said that you rotate about sigma x, you're using the fact that that's a Hamiltonian.
That generates a rotation simultaneously with the boundary spin and the system spin at that
No,
point.
I'm just saying that the place
Yeah,
where you are
I'm using the same structure.
you're using the structure of the Hamiltonian, that only sigma axes are involved.
Absolutely, absolutely.
So in that sense, the symmetry is being used, but not explicitly.
No, I'm just contesting the claim that I have to
So what
rotate
Kedar
it.
is saying is construct something which is just sigma x del I basically.
I'm missing something.
I'll get. Yeah, I'll have to think about it.
I'm missing
Yeah,
something.
yeah.
But I seem to rotate.
You want to
only
say
about
something,
the system.
Siraj?
You can have many Hamiltonians which have the same spectrum, right? Like you are rotating by a different unitary, he is rotating by a different unitary.
Yeah.
So both are symmetric.
Yeah, their
That's how
eigenstates
it's
will be
larger.
different. No, their eigenstates will be different, but their eigenvalues, I think the spectrum all agree, right? So,
Yeah, maybe one more comment that may be relevant is that if you have sigma x and sigma y, you always also have sigma z in the same algebra.
Yes.
So this algebra here is like Pauli algebra with two sigma matrices. So you'll also have a third.
Yes.
And this may turn out to be yours.
I mean, yeah, maybe you are right. Also, because it's an infinite manifold. So what you are saying is some linear combination in that infinite. Maybe there's two ways of thinking about it.
You need to rotate the system spins and.
I still believe there is something off, but I'll think about it.
But Kedar's way is kind of nice because it just tells you that it's
very
to
nice.
the n copies of single
Yeah,
point.
I just mapped it to
physical
one
Hamiltonian.
easy-
Yeah,
Yeah.
just finish direct product with 2
And it makes
d.
it very clear that I can't mess with adding a sigma y in the spin system.
Correct. Correct.
Yes.
Correct.
No, but you see,
Because
this is where we are
rotating-
using that symmetry.
Correct.
Because
yeah.
you may
No,
say
no,
that you are not using it because of that, but that
bound to
also means that
it's
there is
surely
symmetry.
equivalent, but
Yeah.
I'm just saying, in terms of what he's saying, in terms of the algebra, I'm confused.
Yeah, just in this 4 cross 4 Hilbert space, you could just do what you were saying, right? And see how it maps to these 2 cross 2.
Yeah.
I mean, it will.
But there'll be
That's
some.
how it
Yeah,
is
yeah.
also,
Yeah.
No, but what Kedar is saying. should-
No,
sometimes
no,
it's
hang on.
much easier to think.
No, hang on. What did you want to do?
See,
You no, wait. You wanted to rotate
No,
around sigma x, right?
Let me say
He
two
wants to
things.
rotate bounded.
Statement 1, the
Huh.
boundary spins are conserved charges.
Mm.
So I can fix the sector by fixing the
Yeah.
So let's fix the sector.
Yeah.
Plus, minus, plus,
Yeah.
plus, minus, whatever.
Yeah.
Now I go through the chain.
I agree.
Whenever I see a minus,
Yeah.
I go to that side of
Correct.
the
No, that's fine.
system,
That's fine. That's fine.
Rotate by pi about the
Yeah.
x-axis. I
Yeah.
don't
Yeah.
touch
This
the
this
boundaries.
this probably works. Yeah.
Right.
This probably
It
works. Probably works. Yeah. Yeah.
It
Yeah.
also gives this additional piece of information that the spectrum is the spectrum of the uniform transverse field Ising model.
That I was anyway going to say. So one way of seeing why it is uniform is essentially what you're saying. You fix all the spins to +1, and you know that they are degenerate.
Yeah.
So therefore, it must be
That's
transverse
all I'm
field.
saying.
Yeah.
Yes.
Yeah.
So I was just
Yeah.
confused by your formalism, but it's okay.
No, this is going to be important because maybe in this example it is not
There's
important.
more general ways of
Yeah.
doing it.
Yeah.
just to confirm that your rotation will preserve the spectrum but not the eigenstates, right?
Yeah, of course, this can unitary rotation.
Yeah.
No, the point is it does not preserve the eigenstate, but because it's an infinite manifold, it remains a linear combination in that manifold when you think about like this. That's why you are still
But
safe.
importantly, at the end, the spectrum is preserved.
Yeah, because
Yeah.
what I was saying, well, you're in
Yeah.
the ground state.
Yeah.
Yeah,
Yeah.
yeah, the eigenstate stays because of unitary.
So usually.
Yeah. Yeah.
So just
Hmm.
one comment which we were also talking about. So now one feature of the symmetries that to notice is that these symmetries depend on local positions, right?
Mhm.
So usually in physics, when you have symmetries which are local, we think of them as gauge symmetries.
Right.
So you don't think of the spectrum being in representations of that, but because clearly as you increase the system, the symmetry increases, right?
Mhm.
So this is going to give rise to infinities. So the gauge, we think about gauge symmetry because we want to do away with those infinities, which are just
Right.
copies having to do with the
Right. Right.
freedom at every side.
Right.
So could it be that the right physical way of looking at such models be that we have to quotient by all these local symmetries and just think of one single? So in Kedar's point of view, we know that degeneracy is basically the degeneracy of just local flips of this in
Yeah.
some basis.
Yeah. Yeah.
It's like that.
It is
Yeah.
gauge symmetry.
You have
So
added it by
if it
hand.
is gauge symmetry, then the words that you say change, right? Because you don't say infinite degeneracy, you
Yeah.
say single grounds.
Copies.
Yeah. Copies.
Single grounds.
Yeah.
I mean, when it is degeneracy, you forget about copies. Also, you modern
Yeah.
it
Yeah.
out. So
Yeah.
you say single grounds.
So you're changing the model.
Abhijit,
Yeah.
This goes back to the old question.
standard C2 gauge
Yeah.
theories, which spins on a lattice, etc.
Yeah.
If you take the gauge theory point of view, there are no degeneracies, there are just gauge equivalent configurations, you should mod them out. If you think in terms of the local spins, then there is a huge degeneracy. It's a
No,
little
no,
like that.
but
It's pretty much
yeah,
It's a
but
physical question, right?
No, no,
The observables
yeah,
in the
yeah,
box.
yeah.
That's
So when-
if physical things are spins, then there's a, even in a standard Z2 gauge theory, there's a large degeneracy.
Yeah.
In a,
So
No, but
Abhij,
if the system is, your Hilbert space is recovered by just local action of
Mhm.
all the symmetry, all the charges that are associated with local sites, you might as well mod it out, right? So
You
it's
could,
not.
but it's a physical
Yeah,
question. Are you going to allow
yeah. So
operators-
what you are
But
saying
in
is,
gauge theory also we could do that. In the Young's gauge theory, I could just choose not to mod out my gauge theory. I will get infinities.
You could, but you don't have to. And here, you
Yeah.
might say, I'm going to allow operators.
yeah. So what you are saying, Abhijit, is you want to change the model and mod out something.
So
But what I'm saying is I want to think of this model. So
No, no, but
huh.
I'm saying, usually we don't have that choice, right?
Right.
We have gauge symmetry.
Right.
Because otherwise we take by infinities.
Right.
We also say that only some operators are allowed, namely gauge and gauge.
Right.
And here he's going to take the view, or could take the view,
Yeah.
I'm going to allow
Right.
by your definition
Yeah.
non-gauge.
Yeah.
Right?
Yeah.
So it's a difference.
Yeah.
Right, so in lattice models, finite lattice models, I guess it doesn't make much difference. But in field theories,
Mhm.
you don't really
Yeah.
want to work with gauge theory.
Could be, could be,
You don't want to
could
put
be.
gauge symmetry just
Could
with
be.
global symmetry.
But
Could be.
even in a finite lattice model, you could do what
You could do.
Yeah. Yeah.
You could do that.
Yeah.
But what I'm saying is that you are forced not to do that. When you go work with
when you go to the
field
continuum.
theory.
Yes.
Because generally you get copies of the same field configuration giving you the same action. Right?
Yeah.
So you want to
Yeah.
mod out.
No, yeah, you're right. You're right. Yeah.
So,
So
I say this because
So-
in your discussion you pose this as a question, as a
Right.
one of the comments that
Right.
there is a extensive degeneracy.
I
of
understand.
ground states.
I understand.
So depending on the point of view that you take,
Right.
that statement
I
will
agree.
change.
I agree.
That's the
I agree. I agree. So these infinite copies in a gauge theoretic framework, we say they are redundant. Here we are saying they're physical. So it's like just two different ways of saying the same thing. Yeah. So you mod out in a gauge theoretic sense, in a gauge theoretic setting, and here you don't mod them out. Right. Right.
No,
Right.
but if you want to kind of take some continuum,
Hmm.
think about continuum field theories, then I would imagine that you would be forced to mod out.
I don't know. I don't know.
But
Yeah.
Sumira and I have another confusion now.
Okay.
There may be something wrong with what I'm saying. Because you are convinced, you have a proof that there's spin liquid behavior independent of parameters or in some parameters.
No, independent.
Because if Jx is
But it's summed over the manifold. Yeah.
no, but if Jx is much larger than Jz,
Right.
the way I'm doing it, I'm
Right.
not disturb the sigma x orientation.
Right.
Because I'm
Right.
rotating about the x axis.
Right. 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 Right.
And I've mapped every
Yeah.
so
Right.
I've mapped the every
Right.
sector to
Right.
the uniform
Right.
transverse field icing chain.
Right. Right. Right.
Now I know for Jx bigger than Jz,
Right, right, right.
the uniform transverse field icing chain is ordered in this x direction.
Right. Right. Right.
So there's long range order.
No, that is consistent. That is consistent.
Ah.
That is consistent. So in this model, this icing order is not destroyed.
Oh,
Only these ones are spin liquid,
Ah.
which is consistent with.
but
So
in generalizations of
yeah,
this idea,
yeah,
other
yeah,
things happen.
yeah. So we'll maybe just mention one deformation of this, which sort of breaks this infinite degeneracy, just to connect to your point of whether it is pathological, physical, whatnot. So we can. So while things remain solvable, I can take this one only. And I can just add these operators to it. And this still remains solvable. And now you see this is not true anymore.
Correct.
Sorry, okay, you adjust.
Right? So there must not be any infinite degeneracy, and that is not that hard to see. So the ground, so let's just analyze a little bit. So this operator divides that four-dimensional Hilbert space into two separate Hilbert sort of subblocks. So I have plus in x direction and minus in x direction have signs +1 under this, and minus and plus have -1. So this still remains conserved. So therefore you can fix these values.
Correct.
And let's say if this is a ferromagnetic sign, you know that the ground state will be in this sector, right? And so you can analyze a little bit. So we know, so whatever value you want to set. Okay, and then you can ask. So this is another way of saying this equivalence with the transverse field Ising model. You can ask, once you fix this, what does H naught do in that setting? Okay, so let's say I fix.
So sorry,
Yes, please.
for orientation. You say that there's still something that can take for this operator plus and minus at each side.
For which operator?
This sigma.
Yeah.
Plus and minus at each side.
Right.
That commutes with the Hamiltonian.
Right.
So then why isn't there still a 2 to the pi degeneracy?
Because this is not present anymore.
I don't care. I just take plus and minus for this operator
Right.
at each side.
Right.
So then plus and minus at each side have the same energy.
No, they don't.
Why not?
Because of this term.
They are conserved charges, but the sectors don't have the same energy.
Because of this term, Sriraj. No, just
That just means they don't change, right? Doesn't change the energy terms.
just look at
That
this.
doesn't mean I can simultaneously. Oh, it's
Yeah. So just look at
Oh,
this.
sorry, doesn't mean I can simultaneously diagonalize that and the Hamiltonian.
Yeah, I can. But there is this energetic.
Not necessarily. Okay.
There's an energetic.
I see, because you can't change them. Yes, thank you.
Yeah, and now I've just put an energetic cost to having that.
Thank you.
Yes. So let's say I fix. Oh, hi.
Hi, sorry, the camera has gotten blocked. Someone is trying.
Yeah,
Yeah.
You have to move out.
So this is for recording, that's for Zoom. I don't know why two separate cameras.
Yeah, it should be fine now.
Mics are set.
Yeah, it's fine.
Yeah. So suppose I fix the value of +1 to all the bonds. I can now ask what H naught will do, but maybe we can skip the details and we can. I'll just state the result. This actually now maps to a dual Ising model actually. So I'll just write it down.
So this algebra is one-dimensionally reducible at that time.
And the only way, as Sandeep was saying, you will realize effects of this degeneracy is to have non-gauging variant operators. Otherwise, you will just have trivial factors all the time. That's all.
So this spoils the degeneracy we had. So when this term is 0, it effectively maps once you fix. So another way of saying it is the natural way is to fix these boundary spins. But there is this alternate way available to me when I fix these values and don't fix this. When I fix these values, you can check that the action of these terms reduce to an effective Ising model. So it turns out, I think this becomes the transverse field term, and this becomes the Ising exchange.
The values of your other conserved operators, sigma x boundary at that one.
Yeah.
Those values determine whether the field at a site is is in the plus z direction or minus.
Yeah. Exactly.
So there, did you mean del I, sigma del I? Is that
Where?
the next line?
No. Oh, yes, of course. Thank you. So, yeah, so this is another way of seeing the equivalence to a transverse field Ising model. Yeah. Tau is, this Hilbert. Suppose I fixed it to all +1. So I have a two-dimensional Hilbert space on each, on each this, right? So tau is the operator in that Hilbert space. Yeah. So that you are never going to go out of that Hilbert space because this is conserved, right? So in that Hilbert space, it becomes an effective Ising model. The dual nature is what was like the Ising coupling actually becomes the field term, and what was the sort of a transverse field coupling actually becomes the Ising term. So that is a little interesting aspect. Yeah. So in terms of a spectrum, suppose in this case I had all these.
What are the taus again? What is it? Tau?
This tau are operators corresponding to this two-dimensional Hilbert space. Yeah. So there's this. Yeah.
That's called tau z.
Yeah.
You're calling that tau z.
Yeah. Because that's a sort of the. Yeah.
Right. So now tau zi, tau zj will also have this boundary coupling. Sigma x boundary, sigma x.
Yeah, like the link that now you're thinking in terms of an effective degree of freedom on this bond, right? Yeah,
Right.
yeah.
So I didn't understand how this Hamiltonian is that Hamiltonian.
So if I have plus plus and minus minus,
Yes.
right? So plus plus and minus minus, let me think about this. So I have, let's say, plus plus here or minus minus
But
here.
for sigma x.
For sigma x. Yeah, these are x. So when under sigma z, they will flip.
Yes.
So that's like this action on site,
Yes.
right? And now sigma x will care for, say, if you have plus plus here and minus minus here, it will check whether it is plus minus here or plus plus here. So it will give you a coupling, right?
Right, but somehow.
Hmm.
Yeah. Okay.
It's fine.
Yeah.
Good. So, under this deformation, you can, this sort of extensive degeneracy will subdivide into a unique ground state, and then the excitations will, let's say the ground state corresponds to all plus 1. So the excitation will be like, let's say, all plus 1 but one side, right? So there are many such choices.
So like NCM kind of.
Exactly. So it has a very angular momentum kind of feel to it, this infinite degeneracy. Okay, so that's way in which it sort of like there's a striation of this, and then they all collapse onto each other.
I didn't understand this. What is these numbers?
How many, you've got a ground state and an excited state and inside. So how many do you have in the excited state? There'll be LCM ways of doing that. All of which will have the same.
Mhm. So this, yeah,
So how many ways to choose?
right.
So that's coming from
Standard
the.
common
Some LCM.
So wait, so that's coming from the last term.
Yeah, just from the last term. This 2 to the power L subdivides into each binomial sector of, L choose 0, L choose 1, L choose 2.
Okay. So that's the standard, one particle, two particle.
Yeah,
particle
yeah,
execution.
yeah, something like that. Yeah.
And you can do this in any dimension to the transverse realization.
You can do it in any dimension, yes.
I mean, this still does have this symmetry, right? This huge symmetry.
It has this one, yes.
Yeah, local
That-
symmetry.
Yeah.
And the point is that the ground state is invariant under it, is it? Because if it were not,
Yeah,
then
yeah,
it
yeah,
would
yeah,
just
yeah.
act and make modes.
Yeah, it is invariant. Yeah.
And that can follow from this?
Yeah, because I just added that term precisely, no? So it cannot change under that.
I mean, it has some eigenvalue.
Yeah.
It's just a one-dimensional representation. Each state is a one-dimensional representation.
He meant that the state is invariant.
Yeah.
State is invariant.
Yeah.
It's not taken to something else, but it's not annihilated by that.
No, invariant state means just you get the same state.
Shape with the phase, yeah.
Yeah. Perfect. So I think now we are all on board of the basic idea. So now I'll just go to the two-dimensional construction. So we kind of like to have solvable models. So as we said, transverse field lighting model is well known to be, you can work out the spectrum. But from another point of view, you might not want the model to be solvable. So you want examples where,
If the basic idea is that you will take a model,
yeah,
add ancilla,
Right.
and add this sigma z cutting to some kind
Correct.
of charges basically made. And then
yeah.
whether it's solvable or not,
Yeah, you don't care.
basically adding a gauge degree of freedom
Correct.
by hand,
Correct.
you will get this.
Correct.
always.
No, but that's not the basic idea. That could be one way in which you can take this idea. But my point is not this lattice construction. My point is this structure. So I'll not have this structure, this lattice geometry anymore, but
You want
retain
that
this
as
structure.
Yeah.
Okay.
You will want that.
Yeah. So you can do this. So I have another paper where I do play this game. Yeah.
So you want to now implement that algebra in some other way.
Yeah. So, and this will have a flavor of like a Kitaev model, bond dependent Hamiltonian. So let's do a 2D exam. Question? Yes, please.
Structure here.
Uh-huh.
Here you're fixing some of these products of sigma axis.
Right.
And it's just the number of the
Right.
products.
Right. That's all. Yeah.
That's
That's all. Yeah. Exactly. So now let's look at some 2D models where, so I erased it, but the sigma z itself commuted with the Hamiltonian in the previous example, right? So one way in which we say it, that they become effective classical degrees of freedom, because the degree of freedom you can fix it, right? So, but
You mean the boundary sigma?
boundary, the auxiliary spins.
Without adding this extra term.
Without, yeah. So that may not be satisfactory for some. So you would like models where you don't do that, yet have all this happening. So I'll write down such a model. So we have now degrees of freedom at the sides of your square lattice, if you wish. So it's actually a checkerboard lattice.
When you say 2, you mean 2 plus 1.
2 plus 1, yes. Yeah, capital D, small d. So small d equals 2. Small d equals 2, yeah.
I kept wondering why you were saying now we go to do that.
At least I wrote small d, but let me be little.
Defining capital D and small d is a consistent way.
Yeah. So this is the lattice structure. There is a degree of freedom at all these sites. So often the sort of many-body topological order class that I mentioned, which is the string nets or Levin-Wen models, you generally the construction works because they want also, I suppose, solvability. They want all the symmetries to actually mutually commute, which I don't want. So therefore, to arrange for that, they actually put sites on the bonds, so that the natural conserved quantities have 2 spins in common, and then due to the anti-commutation they actually commute. But I don't want that, so I'll put sites, the degrees of freedom on the sites itself. And now we'll write down the couplings. So let's say this is like a Ising coupling in z direction, and this curvy line is a transverse type Ising coupling in some transverse direction, let's say x. Okay, so that's the model.
Okay.
So you have H equals on these squares, all the nearest neighbors, sigma iz, sigma jz. By the way, just I didn't mention that the values of the couplings was not important for any of the discussion. So they could be disordered, whatever. So there, of course, it will matter in the energetics of the Hamiltonian, but the degeneracy will survive.
So what you're doing in that case is example of what Sanjay Moudgalya keeps talking about as commutant algebra, local commutators, and then you get a families. Explicit coupling.
Yeah, I am not too familiar, but I think this anti-commutation business is not part of that story.
No, in the end, it's a question about getting the algebra.
Right. And we can just choose uniform couplings. And now we'll see how the same structure emerges, and this emerges little more elaborately. So the on these plaquettes, the conserved quantity is actually product of sigma x's. Right, because sigma, it of course commutes with all the neighbors. On this, it's always pairwise, so again it commutes. Similarly, on this, it is sigma z. So this is not too hard to verify, and this is a standard trick that any where you play. But because these things are site sharing,
they don't commute with each other.
Yeah. So they are. I'll just sort of write it more generally like this.
Sorry, so this plaquette indicates this product of operators.
This one? Yeah. On this plaquette, I consider this operator. On this kind of plaquette, I consider this operator. They commute with the Hamiltonian, and so this was the reason to have this notation, so that I can sort of say it in a single go. Yeah, right. So these anti-commute whenever they share a site, but there is no effective classical degree of freedom now, because on each site sigma x and sigma z are acting. So now, without doing anything, I can say that this will have an extensive degenerate ground state manifold. Um,
Sorry, but how is
Yeah.
this different morally from just lattice gauge theory?
A lattice gauge theory.
Because there also you would write down some local charges.
Let me think
But
about.
I don't want to think of it gauge theory. I want to think of this as physical symmetries. There also I take a state and then I will act on that and then make say that the ground state has extensive degeneracy.
So lattice gauge. So the way when I think of lattice gauge theories, I want to think I do some local transformation that does not change the state itself, right?
That depends on.
Right. So
I mean, I will
so-
make this redundant formulation with the spins,
Mhm.
so that there is some local charge that is associated to placket or something.
Right.
And then I will just treat all the states as physical states.
Okay.
And all the
I will change the
non-invariant
states.
Yeah,
operators are
I'll change
allowed.
this. Yeah.
I think he's saying okay, you can again have a Hamiltonian defined on some lattice, and it has local site-wise symmetries.
Site-wise or
And
placket-wise.
right, that's what you're saying.
Yeah.
And here also, if I am right, do these box and zeros commute with edge?
Yes. Yes.
So
Yes.
that's your
Yeah.
point.
Yeah.
Yeah.
In that sense, there is a local symmetry.
Yeah.
So
But
that's true, right? I mean, there is a map.
So that's what I was trying to see, that usually it depends on our point of view, whether we want to, if you mod it out, then it becomes a gauge symmetry, but if we don't, then it becomes a theory with extensive ground state degeneracy.
Yeah.
yeah. So
What Abhijit is saying is that you have constructed effectively gauge theory, lattice gauge versions of gauge theories with some degrees of freedom.
yeah. I mean, what?
They have exactly the properties that you were.
No. What is making me uncomfortable
And,
is
the thing about these two operators themselves not commuting
Hmm.
would also be incorporated, because you instead of Z2 gauge theory, you would make a D4 gauge theory, a dihedron group or something. Where
Okay.
they all commute.
okay. I don't know what that is, but
some other non-abelian.
I see. I see. And that will lead. That will still
The
not.
charges will not commute with themselves.
But unique ground states, huh?
Not unique.
If you
Not
want
unique.
After you quotient
After you quotient, it will be
Quotient, yes.
unique or maybe few.
Hmm.
But if you don't treat all of the states as physical states,
Ah,
you would have an extensive time.
So maybe the point of it is that for some reason we want to consider them as physically different states.
So I'm just saying that only the point of view is different from the gauge theory. That's what it
Hey,
is.
what about if I'll play your game, one-dimensional game, and now introduce taus.
Mhm.
Let's say I call sigma x, sigma x,
Hmm,
sigma x
yeah.
on a square.
Yeah.
A tau z.
Yeah.
Right? Then the other term, which is
Yeah.
the sigma x on the bond,
Yeah.
becomes like a tau z coupling.
Right.
And this term
Right.
becomes what?
Uh,
What happens if I think of there's not enough degrees of freedom?
So this is a bigger Hilbert space, right? Because there's a 4, so it's a 16 Hilbert space. So
Right.
under this, so you can play that game if you make these themselves as the operators in the Hamiltonian.
Yeah, that's what I'm saying.
Yeah, you
The
can.
product of the sigma x's is one tau.
No, it's one tau, but it is also the Hamiltonian. If you do this as a Hamiltonian,
Yeah.
then there's a. It's
No, I'm saying take your Hamiltonian.
Okay.
Rewrite it in these variables.
Yeah, so it's a 16-dimensional Hilbert space, right? So say all plus 1 and all minus 1 have some energy. 3 plus 1, 1 minus 1 and 4 choose 1 have a different energy under this, and so on. And then there's a sort of a complicated transverse field type action there.
But actually, can I ask one small thing? I'm a bit confused, which is you may have a Hamiltonian with these local symmetries, but the ground state could still be unique.
Correct.
So, I mean, perhaps the non-trivial point you're making is that you get a huge.
Yeah, so
Gauge theory will not be.
No. How
You always do gauge transformations.
See, but if the unique state were anyway invariant, you wouldn't get even in the extended Hilbert space, you wouldn't get a big degeneracy. You see.
No, but is
So-
that what happens?
Huh?
Is that what happens? I mean, if we write down the model.
But I thought
Could be.
Sumiran's point is that he is getting this big degeneracy.
But I think Abhijit is saying is the Z2 gauge theory that you write
That's
out the
right.
spins will also have.
We'll have,
We just view those as gauge copies of
No, but I mean, maybe the Z2 spin symmetry has a unique ground state. You know, even, you see, the Hamiltonian may have local side-wise symmetries. That doesn't guarantee
Yeah.
that the
So the point, I guess, what
guarantee, but I'm saying generically that will also.
But maybe that's what is being shown, that you do have this big.
you're right. I mean, the flip.
What you said,
agree.
otherwise,
Yeah.
it would have.
Yeah, like you don't mod out everything.
Maybe that's what is being shown. That okay. You can
I mean,
the Z2 gauge theory in 2 + 1 dimensions will have the property of agency, right? I mean, the familiar.
On the lattice, the
Yeah.
usual lattice.
yeah. So the way you generally, I mean, this is not a very unnatural formulation. So that's why I want to think of them as something physical. Like a lattice Z2 gauge theory, you know, you will put some matter degrees of freedom, some gauge degree of freedom, couple them so that you're just like taking actual physical degrees and just coupling it, right? I mean, it's as natural as it gets for us.
Yeah.
You're saying if it was a physical system.
Yeah, it has to be that.
Write your
Yeah.
star operators and the
Yeah.
usual
Yeah.
spin system. There's a
Yeah.
usual spin system
Yeah.
description.
Yeah.
Z2 gauge.
Yeah.
No, but he's saying that if this was really a material, it had this
Correct.
property, then it's not.
Right.
Then it's not a gauge.
Right.
Okay. But I'm sorry,
But I'm saying
No, but it has a flavor.
You could take that.
Yeah, like you take that gauge transform state as a physical state. Yeah.
Maybe I have a naive question.
So
These
Yeah.
things look like matter fields to me.
These.
Do you have? Do you have link fields?
No, only on
so
site.
Only site fields.
Yeah.
So this seems like just matter fields.
Yes.
It's
Yeah.
not, it's not like
It's not obvious. Yeah.
simply
Yeah.
like a gauge.
Yes. So just as a side comment, so just to so if you take the Kitaev model, which is what I was telling you, so that is defined on a honeycomb, and again it has just bilinear spin couplings in some pattern, but this is where right, and you have the conserved quantity is defined on a plaquette, some product of sigmas.
Here you have a similar conserved quantity, right?
Right. This is not the point I'm making, but to see the gauge structure of it, you do a prescription by Kitaev, go into some emergent degrees of freedom, and when you do that, it becomes a free Majorana theory. These gammas are Majoranas, and you have a gauge field, and this is the Z2 gauge field. So the gauge theoretic, and so the product of this Uij's on this is this gauge invariant operator. So these, I want to think of them as gauge invariant objects. So that's where, that's why I want to say that the degeneracy is physical.
Yeah. So just at the technical level here, your circles and your squares are not on the same sort of site, right?
No.
So now there's no, if you try to implement this algebra, you can't do it like a product of algebras.
Yeah.
It's just one big algebra.
Yes.
So it's not totally clear to me that the technicalities are the same as the previous thing.
As this thing?
Yes.
Yeah, it is not. It is not. It is not because these.
1 minute. So you have infinitely many conserved charges here, which are the product of the sigma axis on each square.
Right.
I could either view it like that.
Right.
Or product of the sigma z's on each
Right.
circle.
Right.
I could view that
Yeah.
like that.
Yeah.
But I can't use both.
You can't use both. Here, the point is they all mutually commute. They all mutually commute.
I thought they anti-commute.
No, this is a different model.
Sorry.
So just to, I was trying to connect to Gautam's
But
question
you
of.
also have all of them commuting if I take only the sigma axis.
Of course.
Yeah.
Of course.
So you also have this huge degeneracy.
Of course.
Right?
Yeah.
But if you took only the sigma axis, that would not guarantee a degeneracy, right? That would be
Correct.
a simultaneous diagonal.
Correct. Correct.
You need these other things to get a
Correct.
degeneracy.
Correct.
Yeah. So it's like now a big infinite dimensional algebra.
Correct.
I mean,
Correct.
the representations are infinite dimensional.
Yes, I think so. I think so. I think so. I think so.
Precisely for this reason, it's just because you have a very large symmetry algebra doesn't mean you have a very large ground state degeneracy.
I see. I see.
I mean,
I see.
it's precisely for this reason that I feel,
I see.
the fact that you have this large symmetry algebra is important, but it does, you're
Does not
showing-
imply.
What you're showing is that
Got
it
it.
result,
Got it.
in the system.
Yeah.
you have a huge
Got it.
ground
That's
state
not
Got it.
guaranteed.
And
Okay.
that's the sort of non-trivial
Okay.
for you. the
For me,
result.
yes.
But
Yeah.
we haven't yet seen that, right? You've
No,
not
we
shown-
haven't seen it.
Yeah.
I'm
No,
just
no.
saying.
Degeneracy is seen
How?
because these two anti-commute. That's all I need, like previously.
And then just continue that.
Okay, so let me just be. So just to finish this remark, here it all commutes, all the things. So this is not in that class. Okay, so let's just argue pictorially, say these are all ferromagnetic signs. It stands to reason that the ground state is where the value. Let's choose one of them. Let's say we choose this one. Yes.
At one side, in one circle.
For all circles.
For all circles, to be
Plus 1. Right? So now, Shiraz, I can act by this, the other one, which anti-commutes with this, and create a new ground state. Right?
But first of all, what is the ground state?
What is the ground state?
I don't know. I don't know.
No, but
I don't
it may
know, right?
be, it may be the,
because
Yeah,
it could be that even though this huge group is huge, it could just be a singlet of that.
yeah.
So
Could
can
be,
you
could-
make that argument you are making more formally somehow?
I'm making it. That's what I'm doing. So my ground state, if you give me, which is not unreasonable, is where
No, so why is this +1 +1 +1 the ground state?
Yeah.
this is a intuition. So that it's not important because it's not about ground state degeneracy.
Any state.
Any state has
Okay,
degeneracies.
so let us pick a sector you're saying,
Yeah.
which has some pattern
Yeah.
of pluses and
Yeah.
minuses on the circle.
Right.
Good.
Right, and it stands to reason that if these are ferromagnetic coupling, it will be all plus
So
ones.
that's-
Yeah,
we
that's a
can take a
separate
statement about any
energetics. Yes. So let's
some
take
sector.
this state.
Take a sector. This is a sector.
This is a sector.
Okay.
I take this one, and I've chosen this basis to work in. So I'll act by this on this.
But then you change 4 of them.
4 of them exactly.
Four of them.
So if I act on this, this becomes -1, -1, -1, -1, which is a distinct state.
Yes.
Now if I act by this, this becomes +1, this becomes -1, -1,
Yes.
another distinct state, and so on,
You get a lot.
and so on. It's guaranteed. Yeah.
No, so just to understand,
Sorry.
He's produced raising, sort of raising and lowering.
No, but I don't understand.
the ground
Because
state, sorry, just let me just get one thing right.
Yeah.
You started with that particular sector, everything was +1.
Right.
Now you have to show that it's the ground state of a Hamilton, right? Can you, is that not?
For this, each eigenstate has its
Okay, can you show that H, okay, now I'm sorry to be so slow.
No, it's fine.
H acting on this keeps that sector intact.
because these are conserved under the
They
Hamiltonian.
commute with H.
Yeah.
So the products of this.
Yeah.
So you have
Yeah.
a state which is defined by a sector of the circle.
I see.
You act to it, H on it, you get some. Well,
Yeah.
that's a sector. That's not an eigen.
That's the problem. That's the problem.
Yeah.
I think Sandeep's point is
Yeah.
how do you know the ground state is not invariant under this operation? That's
Yeah.
Sandeep's question.
Yeah.
Yeah.
Could it
What
not
do you
be
mean?
that there is a ground state
Yeah.
which, when acted on by these algebras, just becomes the ground state?
Yeah,
Is that
no,
possible?
this is a very important point.
Sorry, I didn't
This is
follow.
the thing that's
Yeah.
right.
This is
I mean,
Now,
Sorry.
pluses and the minuses.
One at a time, please. Yeah.
Pluses and the minuses define a sector.
Right.
There's lots of states.
Correct. Correct.
There's a particular linear combination we are looking at.
Right.
Of those lots of states.
Right.
and sectors,
Right.
Which is.
I understand. I understand what you're saying.
Now you're going to hit that eigenstate
Hmm.
with the square operator.
Correct.
At some place.
How do you get distinct states?
So now you are saying when I hit it with the square operator, it has the same eigenvalue for sure. Because it commutes with that guy and put it in. Right? That's what you're clear.
Right.
Okay.
So I think what you are saying, if I understood correctly, so when I act by bunch of these things, I get a new pattern of +1, -1. How do I know that's not a new ground
The
state?
mathematical question is, if you can show that this algebra, the whole thing, does not admit finite dimensional representations,
Okay.
then you're done.
Sure. So
Okay.
so let me. But that is.
Why can't such an argument not be made as that you look at the ground state
Yeah.
and that ground state
You
you
just act-
diagonalize this
yeah.
circle operator.
Yeah, and you just act on
In
it.
the eigenspace you diagonalize the circle
So
operator.
I think his argument
It's a
is-
commuting. It commutes, so you can diagonalize.
So
it.
let me again say it. Let me say it in this sort of more formalish.
I didn't understand. I didn't. Let's just explain it.
So,
Who explains it?
please.
Yeah. So this is what I think, Kedar, you were right. Right. So psi and b psi are partners. Right.
psi is an eigenstate and you are labeling it by A.
Yeah. So
Is
this.
that what you're doing?
Yeah.
There are AIs.
Let me put the question like this. You see, it's true that
Yeah.
the box operator, okay, can move you around.
Correct.
But I could generate the following state. I start with everything plus 1,
Right.
act with it with all possible box
Right.
operators in a linear combination.
Right.
Such that now it's invariant under all box
Right,
operators.
right, right.
And declare that's my ground state.
Yes, yes.
Now you may have a unique ground state.
No, but
How do you know? How do
No,
you
but
know?
in a one eigenspace, why can't you diagonalize, let's say, well, pick one set, let's say circle set.
Yeah.
Why don't you diagonalize that?
Yeah, you diagonalize it.
That's a
but
basis.
You know, you
In
diagonalize
the
it.
eigenspace, in the zero energy
No, no,
eigenspace.
what you're saying is right.
States
So
in
So
that
let
sector.
me, let me make a
There are
point.
many
So,
states in that sector. How do you know the ground state is not unique?
In fact, those eigenvalues are not the eigenvalues of the Hamiltonian. because
so the
these are
linear,
not
the
common.
particular linear combination, you are agreeing with whom?
I'm agreeing with that.
Okay, good. So Sandeep.
Okay, go ahead,
So
please,
so we
please.
remember we needed this to be non-zero.
Psi was what again?
Psi is some state
Okay,
which
some
has
state.
eigenvalue
It's an eigenstate.
a under a.
Wait, so
And
it's
A was
eigenstate
what
simultaneously
just
or
defined. Please, it's one of these two operators.
One, let's say one. Just more formally speaking.
So it's a simultaneous eigenstate of A and A.
Correct.
Okay.
Very good. Now you wanted a linear combination of those states. If it is a uniform linear combination, then you will ask what is a under that, and that will actually be 0 because you have combined over everything. So that's one way of thinking why it is a unique
The way
state.
I was thinking was, we go to the sector where the circles have value plus 1.
Correct.
Fine.
Correct.
Now there are many states in that sector.
Correct.
No, I think start with some energy eigenspaces. Start
Okay,
with those
let me
eigenspaces.
pose it this way, then you tell me. Now, okay, there are many states, right? Okay, now you can perhaps go from one state to another in general using your square operator.
Correct.
Right?
Correct.
That is
Correct.
the
Claim.
basic thinking.
Yeah.
Okay, fine. But how does that prove that the ground state, which is some linear combination of all states in any choice of basis, is not unique?
A linear combination of the spin variables.
Of all states with zeros taking value plus
Abhijit
1.
has a great idea.
Okay, give it.
Okay, please.
Please give me.
I think it's clean. You just start with an energy eigenspace. A space of all the states with a given energy E.
Okay.
Now, because H commutes with all the A's, you diagonalize in that eigenspace A's.
Is
All the
call it
A's.
circles.
Circles.
Simultaneous
Yeah, I'm happy to
eigenstates of
diagonalize
circles
a circle.
and H.
But in the ground state.
In the ground state.
So simultaneous
Subspace.
eigenstate of H and circles
Yeah.
is what you're looking at.
Yeah,
And you're acting on it with a square.
Yeah. So you just look at the zero energy eigenspace.
And
Okay.
square annihilates it, I claim.
No,
It moves it.
moves it to a different sector.
Why does it follow?
Square can't have zero eigenvalues, I think, right? Is that
Square has plus minus one
Plus minus.
eigenvalue.
And on any eigenstate, he's shown us how square acts.
So the point is square changes the sector of the circles.
Yeah.
And changes it sort of point by point, so it's extensive.
That's right.
Yeah.
So square can't leave this particular state invariant.
Yeah, he's
Yeah,
shown us how it
yeah.
acts on these
Yeah,
states.
yeah.
Square, yeah.
Not really, because it could have been a linear combination.
No, but on any given eigenstate of circle. Because as Abhijit said, we can simultaneously diagonalize energy and circle.
So we
So
have
we
some
go on particular eigenbase.
we have an eigenstate labeled by circles.
Circle eigenvalues.
You act on it with square,
And now you
give
go to another.
different values for some circles.
Yeah.
Right?
Okay,
And this is also an eigenstate. And by
It's also an
construction, it's a different
eigenstate. I
eigenstate.
act on it with square again, and I keep doing it.
And it's a
It is linear
eigenstate with the
combination.
same energy.
Yeah, and I take a linear combination.
Then
This state.
if you take a linear combination, then it is not an eigenstate of A anymore.
So then you're
Why
fully
are you not
destroying
changing
something.
circle? for-
No, you can mix A and minus A state, na?
Circle plus. Oh, circle doesn't commute with that.
Yes.
That's it.
Yeah, that's the
I
point.
think that's important.
That is important. That is important.
That
Yeah.
is one of the
Oh, that's the.
So that is the new structure that I'm trying to emphasize.
That's your new structure. Circle doesn't commute with that. It
Yeah.
anti-commutes.
It anti-commutes when they share a site. And the point is, this is not an unnatural structure in spin models.
I think this was the structure I was missing. It anti-commutes.
Yeah, that
If it had commuted, then it would be okay. It anti-commutes.
Yeah. So all the many body topological orders don't have this structure. They always have commuting structures.
Yeah.
Okay, so
Because this is how one would build the kit. I have a ground state, right? You take the star operator, diagonalize it.
Yeah,
They
yeah,
were saying,
yeah,
but
yeah.
If you take the star and
Right.
bracket, they don't commute.
yeah, yeah,
You would
It's very
actually do the
similar,
same.
yeah.
yeah, yeah, yeah.
No, but I mean, the star and the plaquette commute with each other. They are
Yes.
and here
Yes.
they don't
commute.
That's the new structure.
That's a new structure.
And
Precisely.
it's also important, I mean, it's very important that this box and circle can't have zero eigenvalues.
Zero eigenvalues. Yeah, from a mathematical point of view, which is very natural for Pauli operator.
Sure, of course,
Yeah.
I see. Okay, thank you guys. Sorry.
Very nice.
Very beautiful.
Yeah. So now, so the entropy counting is somewhat simple. Although, so here it is you take one set to diagonalize, and the count of the other set gives you the degeneracy count.
Count of the other side?
Because I can act on this to get a new state, I can act on this to get a new state, I can act on this and this to get a new state, and so on. So you get 2 to the power.
Whatever you act on is different.
Yeah.
Say again. Sorry, just once more.
This was the
There
same.
are some, if I act on a bunch of them,
Forget periodic, infinite lattice, let's say.
infinite.
So that means
Okay, there's
each
no
energy
limit.
level
Yeah,
has a
yeah.
degeneracy.
So the scaling is.
Scaling is fine.
Yeah.
I mean, each energy level has a degeneracy given by 2 to the n,
Number
where
of
n is the number of squares.
Squares. Yeah.
It's
Yeah.
similar to this is
Yeah.
2 to the n copies of a single chi basically.
Right. So the entropy is n log 2, and where n is the number of.
I guess the only confusion I have is each action of a box changes 4 circles.
Yeah. Very good.
So in the actual coefficient, it's going to be proportional to the area, but the actual coefficient is something I can't see.
But I think the claim is, you say you start with all classes,
Yes.
and there's no action, no simultaneous action of boxes that will take you to the same state.
Yes.
For infinite lattice.
Therefore, each action of a box takes you to a different state.
Yeah.
Each action of a box takes me to.
Because if that was not true, then some simultaneous action of boxes should retain the state.
So without periodic continuity.
Yeah. In fact, this is the same.
You'll have some.
Yeah. The scaling remains. So.
I still don't quite, how do you know, how do you know that a action of a set of boxes doesn't retain the state? Because it can't have eigenvalue.
Right.
He's just showing us that.
No, but that showing us is a bit deceptive, because you can have a linear combination of, having you could have a ground state which is a linear combination of circles
Sandeep,
plus and plus
No, but Sandeep, you can simultaneously diagonalize circles and energy, no?
Yeah, you can.
Why should you make
So you just work with that basis.
Yeah.
It's your choice.
He's going to show us that every single possible value of circle, eigenvalues, you can make by acting with boxes.
Yeah.
And it's, I think, pretty easy.
Yeah.
Sorry, say again.
Say, start with one set of eigenvalues for circles.
Yes.
And at a particular energy. Now he's going to show us that by acting various boxes, he'll make every single possible set of eigenvalues for circles.
Yeah.
And the initial.
Thank you.
So,
Every apart from age effect.
Yes. Okay, fine. Now I agree.
but is it clear
You start
that
from plus. You will not change the sign of the product of the.
Oh, maybe there are two sectors.
Yeah, there's some several sectoring. There is some sectoring.
It's proportional to area, but we don't know the coefficient.
There's a sectoring effect. Yes.
But I think of the proportionality to, once you take the log,
Yeah.
that will be log 2.
Yeah.
The proportionality.
Yeah.
These will be like finite
Yes.
effects in log.
Yeah. And that is the point.
by
So.
the way, this does have a feature, kind of flavor of some gauge loop, right? Because because when you act these processes, only the boundary of that matters. Where you switch from plus signs to minus signs.
So it has flavor of that, but these are physical also. Yeah. So one simple limit in which you can see the degeneracy obviously is you just take one coupling to 0, and then the 2 to the thing becomes evident.
So one question. So let's say you diagonalize energy and A's, right? Like the square circles.
Right.
In that eigen basis, is there degeneracy further?
There could be.
So one doesn't know in this model.
Like from this structure, I can't say anything. Yeah, there could be, but this is enough to guarantee this. Yeah. So there could be some additional sort of prefactor there.
That will depend on details.
Details. Okay.
Maybe counting of input space dimension will also tell you what it has to be.
Right. So even though the entropy or the degeneracy counting is quite straightforward here, the reason to mention it is that in some situations it can. Yeah, please.
Suppose I use periodic boundary condition, and then I can think of like a Wilson loop. Like
Correct.
For product of squares.
Correct,
from a
correct,
boundary.
correct,
And
correct.
That also preserves the
Right,
again,
right.
the state.
So that's what Keda was saying. So these are edge effects. So it won't, so just think infinite. That's why I'm saying, just think infinite, you necessarily have log 2 per unit cell.
That is coming from,
Hmm?
that is because each square can change it to change 4 squares.
Right. So entropy is n, where n is the number of squares, I think, minus some finite correction which does not have n dependence. Okay.
That is
Yeah.
the boundary.
Yes. Yeah. So, but the entropy counting can be little more non-trivial. So there's another model in my paper which has it. So maybe I can try to draw it. Sorry. So these are, let's say, sigma z's. Then these are sigma x's. Some checkerboard pattern of this sort. And then you connect. Okay, I'm drawing it wrong. Let me just look up my paper. Right, sorry. So this is our circle actually. And you imagine this pattern going everywhere, and then you will connect this by circles and this by straight lines. Straight lines, circles, circles, straight line, and so on. Okay. So here also the same thing is happening. Okay. Here there are more kinds of conserved quantities. Okay. So you have these conserved quantities on these sites. You have some conserved quantities on these things as well. Okay. And now how you.
So just to understand, what are these lines and the curly thingies? There's some
Yeah.
terms in the Hamiltonian.
Yeah.
Is that right?
Yeah.
Oh, okay.
Yeah.
But now they are placket or circle.
Yes.
Not
Yeah.
not our side.
Yeah.
If I understand.
Correct.
Okay.
Correct. No. So these are all just two spin terms.
Or they're still two spin.
Everything is two spin.
Types of two spin. Curly and.
Curly is sigma x, sigma x.
Acha.
Straight is sigma z. So it's the same kind of thing in a different geometric setup. It turns out, apart from the placket conserved operators like this, you have also conserved operators here. Right. And then you have to put a little bit of more thought of what is the degeneracy guaranteed by this, and so that's pointed out in the paper.
Is there so in the previous example you could map it to a canonical Hamiltonian spectrum you then knew, right?
Right.
So here is there something like that?
No,
Okay,
it's
so
not
hard
known.
to say the spectrum.
Yes.
Just know the degeneracy.
Degeneracy. So degeneracy we can like this is the degeneracy owing to this structure. There can be some additional degeneracies which we can't predict from this.
Sure, but it's at least as big as that.
As big as that. So this is where, so this infinite, this extensive degeneracy cannot be allowed for topological order. That's this Haas bound that I was saying. So it's not obvious. And
and for you, just sorry.
Yes, please. Please.
Would that mean if I put this 2D system on a torus, what would happen? You continue to get the degeneracy from your argument.
Yeah. Some finite order 1 corrections, but you have the degeneracy.
So it's some gapless system even there.
Gapless in this sense, yeah.
Huge downstate degeneracy.
Correct. So what is this beast is not clear to me. One comment is, so the nature of excitations that we are talking about, you see, so all this discussion never cares about the couplings. So it's clear that say this coupling was turned off, then modulo this degeneracy, it's a gapped spectrum, right? Suppose I set this to 0, then I just look, or let's say I set this to 0, then I'm just focusing on the circles. So on the circle, this term has some dispersion, some levels, right? So let me just, on a circle, I have plus in the x direction, and minus in the x direction has, I guess, 4jx, then plus minus, and its other partners have 2jx and so on, right? So you see, and then when you turn this on, when turn that on, and so the degeneracy is clear.
Plus and minus is in what basis?
In x basis, or sorry, x basis. Yeah, so it is a little confusing. So you see, so that this degeneracy is clear. Each state you can choose. You have two possibilities for this. In fact, this and so on, right? So in fact, you have additional degeneracies you can kind of sort of see from this in this limit. You have 3 plus 1 minus and then 3 minus 1 plus and all the symmetry related partners. It is not obvious when you turn this on that 6-fold degeneracy breaks down into 6 different states or 4, 2 or whatever. So there could be additional degeneracies. But it is sort of clear that this sort of spectral structure won't immediately close. So when Jx and Jz are not equal, there is a gap to the spectrum modulo this extensive degeneracy. And when Jx equal to Jz, you would very naturally think actually the gap closes and you go to the other side. Yeah. So that is intuitively clear, but how to sort of say more than that is not clear. Yeah.
Suppose, just going back to the simplest of these models, suppose now you turn on a little bit of an interaction that breaks this symmetry that gives you this.
Right.
Now you have some very interesting dynamics in this
Right.
band of states.
Right.
Is that something that has been looked at?
No, it's.
So you might get some completely non-trivial dynamics.
Sure,
because
sure,
things
sure.
are basically
Yeah,
degenerate,
yeah.
then you
I agree.
And then also, in that situation, Abhijit's objections go away.
Yeah. Then they become physical with their energy scales, time scales, and so on. Yeah. So that's where these sort of speculations about chaos propagation and all that were coming from, actually. So it's not known. Yeah.
It's a little like SYK in that sense, right? I mean, SYK in some sense,
except so that's what I'm not able to pin. When you want to say it's SYK like, but what I'm told is, so these are like guaranteed degeneracies. Even when you break them, you have a unique ground state, then you have a sort of large degenerate thing, then this L choose structure that you can't get rid of.
Let me just say once again, I mean, in n equals 4 angles, for instance, in free theory, we put these large degeneracies. Okay. Now, in a sector that, just looking at things that look sort of supersymmetric at zero coupling.
Okay.
Now, if you turn on a coupling, some of these states stay degenerate.
Okay.
But then there's very interesting dynamics between the band of states that are lifted.
Right.
And these are supposed to produce near extremal black holes.
I see. So yeah, it's quite possible. It's quite possible. It's quite possible.
Directly in the SYK.
It's quite possible.
You have a unique ground state, of course, if you do it in the proper limit.
Right.
But the spacing is exponential.
Exactly. Right? That is the point. Yeah.
So if there was a sense in which, if you put the system on a finite lattice,
right.
If your breakings were very small,
right, exactly.
That might be
there's a slight distinction. So SYK is, so let's try to draw it. So I think drawing the histogram is the best. So this is like a histogram versus energy. So energy is here. So SYK, let's say, does this, and just for comparison, non-SYK.
What's on the x-axis?
Number, some histogram. You kind of get this exponential suppression in the density of states. Okay, so this is the generic situation, and SYK avoids that. Now, so what we have is by construction the same amount of degeneracy in each state. So that cannot affect the histogram because it factors out.
No, but once you break, after the breaking.
break करने के बाद.
That's the question.
Yeah.
Right.
How small is the space?
Right. Thanks. Yes. Thanks.
What are the interesting ways of breaking?
The simplest interesting way of breaking is you just add these terms.
No, but you might have a particularly nice way of breaking.
Maybe take random.
Something like that.
You take random, or you just add these to them.
Just to say again, in n equals 4 angles theory, we have these very large degeneracies in free theory.
Okay.
And then some of it survives.
Okay.
Because they're supersymmetric, and then you get break. And as I said, this produces very interesting geometry.
I see.
It's a very particular way of breaking.
Okay.
So it's a, which produces very interesting effects.
SYK, if I may ask, I don't know, it's a bit of a off topic, but If I may ask, I mean, how does this controlled this thing happens in such that these ground states still have interesting dynamics near it?
Even why is there such a small splitting?
Such a small splitting.
This is coming from some random matrix theory business, which
that's why I was thinking maybe taking random.
Some random couplings.
No, but I guess this is true for each instance of the coupling. Right?
Yes.
It doesn't depend on, so
it does not depend on coupling. Yeah.
But maybe your point is take the breaking to the
And
then you just reduce it to a matrix problem where you have a large matrix.
Correct.
The leading
Correct.
order is
Correct.
degenerate with
Possible.
small terms which are random.
Possible.
And then it's a
Possible.
random but not every random matrix theory, of course,
Right.
gives the
Right.
SYK
Right.
story. So
Right.
you have to choose.
it's robust in some sense.
It's robust in some
As
sense
long
that,
as you have this.
if you have the same double scale, if
You-
you have the same behavior near the Wigner
Yeah,
square root,
this one, this
you
one,
need
this
a
one,
characteristic
this one.
right behavior.
If after breaking you can get an interesting chaos exponent,
Yes.
that would be a good diagnosis.
Exactly. Yeah, or even the level statistics. Just look at the level statistics.
It's
Yeah.
better to do the level because
Yeah.
that's very
Same.
What happens that every second state also has this degeneration.
Correct.
It is not true and
No, but that informs the histogram, na?
Let's make a large gap. So separate. For instance, let's say we're only interested in the dynamics around any one. Forget
Yeah. Well,
So
I
just
agree.
to say,
I agree.
At least the Wigner ansatz is too crude a diagnostic.
I see, I see.
The Gaussian unitary
see.
ensemble also has Wigner statistics.
Okay,
And the
okay.
SYK
Okay.
also does. So
Actually-
you need more than that.
True.
You need
So,
more than that,
so-
but it's easy enough, to check from the density of state.
yes.
So
So,
I would just go with that as a diagnostic.
yeah. So this is all. These kinds of diagnostics are described in this review of Chaudhary, Parcolet. Are you aware of this?
The one
Yeah, Devanjan,
Sudev, right?
Sachdev. Yeah.
But I'm just saying of them all, practical terms rho of E is the
Yeah, of course, if you can, but the point is you have to measure the spectrum. Okay, I guess with the low energy spectrum, you can already say some things. So one interesting diagnostic that is mentioned in this paper connects to this partition theory of Ramanujan and Sol, which I was telling Kedar. So which really is sensitive to the fact that whether there's a quasi-particle description or not. I can't give you the details, but it's talked in this. If you have a many-body eigenstate, you can ask the question, can that many-body energy eigenstate be partitioned into individual single particle eigenstates? So for just by consistency conditions, all states should be partitionable in some unique way. Only then it may be consistent with the single particle spectrum. And through this partitioning theory, you can come up with a diagnostic that this detail I don't know. Something about the density of states, some moment or something should be a certain number based on partition theory.
That guarantees exponential small space.
Yes. So you can check for that number. So this is a very interesting diagnostic. It's in this.
But I mean, more dumbly, just put it on a L by L and see after small breaking. I mean, it's not so bad.
Yeah, no, that is one of the things I am doing. So from that point of view, already I can mention one thing. I wanted to do the spin liquidity proof. Yeah.
One question, since you have all this large degenerate spaces, presumably you can still have large enough but break it in some
Right.
Is it possible to think of non-ability whatever braiding kind of things if you think of some ideal definition in this?
Yeah, so for that one needs to know the nature of the excitations.
Yes.
I mean, it's a related question.
Yeah.
Yes.
I mean,
I don't know.
Just to say, might be a little bit extending what's true, but if your spectrum doesn't have that exponential growth of SYK, then it's almost certain that it's not going to have the dynamics due to the Schwarzian mode and so on.
I see.
Yeah. Because that just for the density of states follows from the Schwarzian.
Yeah.
So then one would be willing to bet. I would be willing to bet you won't saturate the chaos bar.
Yeah. It's possible.
Density of states is this usually
correct. Yeah, but it could still be between. It might not be T square, a temperature square, not temperature, but maybe T to the 1.1. Who knows? I mean, so that depends on details.
It could be.
Yeah. Not saturate, but sort of not quite not Fermi liquid like either. Yeah.
So actually, this low energy dynamics of the SYK can be then in thought in terms of the gauge theory point of view, right? That you had to begin with some gauge, I mean, this reparameterization invariant, and if it were exact, that would be the gauge symmetry, right? But now it's broken, so it ends up being some sort of a sigma model on an action which is not zero on the gauge transformation, but it's what is preserved is only the global part.
And
so
it's
in
the
that
lowest
sense,
dimension of it.
So in that sense, one can guess something right here that now this symmetry that the given degeneracy is all these squares, right? And then you basically break that.
Right.
So
But the map between this and diffeomorphism is very non-trivial.
not diffeomorphism, but at least it's local in some sense. It's local.
But one thing that's going to change here is that it's local also in space.
Local in space, exactly.
Which was not there in SYK.
Yeah.
So it's going to be straight.
Somewhere in between. It's a new beast is what I believe. Yeah.
It's not so easy to map this to at least what I was, the diffeomorphisms.
Right. But let me
Product of the sigma excess on the mixed placket, the thing with two arcs and one square.
This one?
In the left, the simpler problem. Not in the.
Here. There's no obvious conserved quantity associated with this.
So the sigma Z coupling doesn't change that product of sigma X.
Hmm.
And the sigma X coupling also doesn't change it.
Okay.
Why isn't that conserved?
Which one?
So
Oh, you're saying sigma Z, sigma. So
sigma X, I'm missing something very. You said sigma X is conserved on a box.
right.
I'm saying what about on a placket which has two straight lines and two curves?
Sigma X is conserved.
I'm asking if the product of sigma X on a box which is on a placket which is two straight lines and two curves.
No, it does not commute with this. Say this one. It does not. Right.
So in fact that's, I see. Okay, very nice.
I mean, what
It flips. That's a flip, right? Okay.
But there are two sides.
Good. No, but each is individually acting. It flips.
Yeah.
Good. So then what about a change of variables? So I need how many Pauli matrices, as many as there are sides.
Mm-hmm.
So I take each of my squares
Mm-hmm.
and I put Pauli matrices on them.
Mm-hmm.
That gives me 1/2 of them. I mean, I'm trying to make a local Hamiltonian out of this.
I mean, this is the local Hamiltonian, so I'm
So
confused.
I'm trying to make it where some of the structure is somehow less. So if I define taus to live on the centers of all the
Mm-hmm.
boxes.
Mm-hmm.
Okay.
I just want to say one last thing. In terms of trying to map to a random Hamiltonian, it doesn't have to be random. It's just you have so many states.
Right.
But there, I mean, what you can learn by just studying random Hamiltonians is that, the kind of Hamiltonian we need for SYK is very non-generic. Because a generic Hamiltonian will give you Gaussian unit rings, which is not at all unique.
Right.
So typically, I would think if you turn on interactions, you're not going to land on SYK like that. You have to do. But if you tune it enough, you will land on it.
I see.
But isn't there one additional element here, which is the locality in space?
Yes.
But I thought, okay, let me put it like this. You can correct me. We had all that, and finally we have some number of nearly degenerate translates. Now I forget about how we got it, right? Now we just have this sector.
Correct.
And I think of small couplings in this sector.
Yeah.
Now I've just mapped it to a matrix theory.
Correct.
Okay. Now, of course, you might ask, do those couplings come from an underlying? That I don't know.
Yeah.
I'm just taking that.
No, I understand. It need not reduce to SYK. Yeah.
I was wondering whether the Goldstone modes would be Goldstone not just in time but also in space. Approximately. Yeah, so it might be just totally different universality.
Yeah. I think it's sort of in between a spin liquid and a.
Stanford Witten papers, right, which had 1+1 dimensional models with SYK-like behavior, which had some of this property. I was wondering whether this might be modeling that.
Those properties have locally large Hilbert spaces. Right? Here, the Hilbert space is not locally large.
But it could be so there's this whole business in lattice gauge theories.
Here, locally, everything is very simple. No, I'm not talking about those. I'm talking about conformal field theories.
Okay.
With 4 sigma couplings.
Okay, I am not.
These models that you can solve by the same techniques, the same Mellon graphs.
You explain no quadratic kinetic energy term.
Like that. The
Mellonic stuff.
Mellonic stuff. They found some field theories which were well defined, right, and supersymmetrically there. And it was sort of non-intuitive precisely because of this, that you might have expected this stuff in space as well as.
Could be.
Is there a sense in which you have sort of sectors of fixed translational, some discrete translations and so on here?
Yeah, if you have uniform couplings, you will
so your
have
huge ground state.
Yeah. But that is sort of fine-tuned, right? Because these couplings need not be translationally invariant.
No, let's take it to be
at least on the average.
simple.
Right.
Then you'll have sectors.
Yeah.
So despite having that momentum.
So another way of, I guess, saying is that they can't sort of transport, even though they are energy, they might transport momentum, but somehow energy does not get transported, maybe, is one way of thinking about it.
Sorry, Shubin, another place where we have large degeneracies is sort of like Landau levels.
Right.
Okay, so just out of sheer ignorance,
right.
If you take a Landau level,
right.
let's say
right.
Landau level, the ground state,
right.
and then you turn on some interactions.
Right.
Does one get? There does one doesn't. One
so
gets like
you don't get this,
effect, right?
but you don't get this. It's not.
Get completely different kind of physics.
Yes.
Gaps,
Yeah.
states,
Yeah.
Quantum Hall effect.
Correct. So this is not that. So I guess in the interest of time, I can just summarize and not get into the spin liquid proof, but just state what the proof result is. So essentially, you can prove that any. So let's just focus on this. I take any two sides far away enough, but they can be somewhat close also. So this is also true of Kitaev models, by the way, but here you can prove it through this structure. Take any index for 2-point correlators, and so this means an average over the ground state manifold is 0. This is provable.
What is this? Just repeat.
So I want the expectation value in the ground state manifold of a 2-point function.
I see, averaged over all
ground states, all states. Right.
All states.
Yeah, and because of this sort of structure, you can show that there is a cancellation happening. Huh? Yeah. So the result for higher order is so let me write down the non-zero ones. So if you want a non-zero correlator.
Sorry, but what do you learn from this? The fact that there is 0. That means.
So this is interesting for condensed matter people because it means there is no magnetic ordering.
Okay.
There is no spin ordering.
What is the role of the fact that it's a ground state? Isn't this true of any eigenstate?
It's true of any eigenstate. It is true of any eigenstate. So that is indicative that there is a fractionalization probably at play here.
Right.
Because it's true of, say, for example, the Kitaev spectrum as well.
Right. What do you mean fractionalization?
Meaning this little detour I went about the Kitaev spin liquid, right? So the degrees of freedom are not natural, some fractional degree of freedom which has a fractional quantum number compared to the spin quantum.
Does this being 0 in all eigenspaces, I mean, somehow suggest that?
Just experience, yeah. So the non-zero multi-spin correlator is, say you are interested in these two sides just for 2 point, take this and 4 point correlator. Nearest neighbor. So you will go to ij, you will see what is the bond there. So here it is XX, so you put XX there. KL, if it is, let's say this one, it is ZZ, you put ZZ there. And only this can be non-zero. Any other combination of is 0 by cancellation. So this means that there is no symmetry breaking that is happening in this model. So in that sense, it smells of like a spin liquid, but what are the excitations? Those are open questions. Right. And I guess I can end it here maybe. So those are the open questions. It's discussed in the paper, the final section, all these kinds of, whether it has some like these near extremal black hole type descriptions or whatever from the quantum gravity side, much more sort of physics questions which are the nature of excitations, what?
With those questions you just map to SYK. So if you get that, you get it.
Right. Yeah, you study level statistics, and there are things to do.
Or just the, the density of states and all.
Precisely. Yeah. So there are some well-defined paths to follow up. Then one more thing was, so what is the consequence on the dynamics of these large degeneracies, like just OTOCs or something, chaos propagation, or even physical sort of propagation of energy or spin. So those kinds of questions are not known, the answers are not known. And yeah, that's about it. So thanks a lot. I think you guys spoke more, which hopefully means you were interested in this, and I spoke less means not much is known, which should be good news for the students. Please, if you get interested, you can. There are many things to be done. Yeah. Thank you.